Now we're going to take a look at the general solution for an overdamped second-order differential equation. So we've established that our general second-order equation model can either be written in this form or in this form right here. And we also know that in order to completely solve the differential equation, we need to have an initial condition as well as a derivative initial condition. So either the, this one is supposed to be V naught right here. So we need to know the initial position of the system, if you will, and the initial rate of change, or the initial velocity of the system. So in order to solve this, the other thing that we need to keep in mind was the previous discussion about the value of the eigenvalues. What types of roots to the characteristic equation do we have? So the first case that we're going to look at is what happens if the roots of the characteristic equation are such that lambda is the characteristic roots are real and distinct. All right. In that case, if we have real distinct roots to the characteristic equation, we know that that comes from the case where the damping ratio is greater than 1, and that also means that we have an overdamped second-order system. Okay. Now, from that, now that we know the eigenvalues, or the roots of the characteristic equation, we also know that since this is a homogeneous equation, the only thing we need to solve for is the homogeneous solution. Once we have the roots of the characteristic equation, we know that the homogeneous solution is going to take the form of the following. We're going to have an unknown constant times e to the first eigenvalue times time, plus a different unknown constant times e to the second eigenvalue times time. All right, and remember that the eigenvalues are going to be given by the equation such that we have negative squiggle omega n plus or minus omega n times the square root of the damping ratio minus 1. All right, so we have our plus and our minus here, which is going to give us two distinct characteristic roots, and those are what go here. Okay, so if that's the homogeneous solution, the only thing that's left to do now is to apply our initial conditions to determine the value of these unknown constants a and b. All right, so if we have, if we assume that our initial condition is some value x naught, and our derivative initial condition is some value v naught, then we can apply the initial conditions and determine the values of a and b. Before we do that, I know that I'm going to have to substitute time equals 0 into my assumed solution for the homogeneous solution here for the derivative. So I need to take the derivative of my homogeneous solution in order to apply the initial conditions. All right, so the derivative of the assumed homogeneous solution with respect to time is going to be lambda 1 times a e to the lambda 1 t plus lambda 2 b e to the lambda 2 times time. Okay, so now I'm going to go ahead and apply my initial conditions. By applying my initial conditions, I know that at time equals 0, e to the 0 is going to be 1, so I'm going to be left with a plus b. And I know based on my initial conditions that at time 0, this position must be equal to x sub 0, or the value must be equal to x naught. All right, I'm going to do the same thing. I'm going to evaluate the derivative of the solution with respect to time at time equals 0. And when I do that, again, e raised to the 0 is 1, so I'm going to be left with my first eigenvalue times a plus my second eigenvalue times b, and we know that that must be equal to v naught. Okay, so now I have two equations for two unknowns that can be solved by substitution to determine the value of the unknown constant a and b. All right, so what I'm going to do is I'm going to first solve a, and A is going to be equal to x naught minus B. All right, so now I can plug this value back into this equation here. So I'll have lambda 1 times x naught minus B plus lambda 2 B is equal to V naught. And now I want to collect my B terms, so I have lambda 1 through distributing minus lambda 1B plus lambda 2B equals V naught. All right, and then I'm going to pull the B out of here. So I will have lambda 1 x naught plus B times lambda 2 minus lambda 1 equals V naught. All right, and then I can go forward and solve for the value of B. All right, so B will be V naught minus lambda 1 x naught divided by lambda 2 minus lambda 1. All right, and then I can now substitute that back into the equation up here to find that A is going to be equal to x naught minus the quantity of, or the fraction of V naught minus lambda 1 x naught divided by lambda 2 minus lambda 1. So that gives me my value of A. All right, so now if we can establish that we have a general second, or we can establish the form of the general second order differential equation for a system, if we can come up with a differential equation model, now we actually don't need to go through this entire process of determining the of solving the differential equation. We know that in general, if we can determine lambda, the two eigenvalues or the two characteristic roots of the system, as well as determining the initial condition and the derivative initial condition, then we can go forward and calculate the unknown constants A and B and just plug them into this general homogeneous solution right here. So again, we need to determine if the system is overdamped. If our damping ratio is greater than 1, we can determine the eigenvalues using this equation right here. After we determine the eigenvalues, we can substitute those eigenvalues along with the initial conditions into these two equations, and then substitute those values back into my general homogeneous solution form. And all of this is in your packet for the Engineering 313 course on page 124 that describes the overdamped source-free second-order system with the generic initial conditions. So again, we no longer need to solve differential equations if we recognize that it's a homogeneous system and it's overdamped. If we can determine the initial conditions and the eigenvalues, we have everything that we need to know to go ahead and write the general solution.